Hi everyone. Today we are picking up where we left off discussing asymptotic analysis. Last lecture I told you about big O notation. There are a couple of other notations that follow really easily once you know big O. There's one that's basically the opposite of big O. It's called big omega notation. And here's what it looks like. Here's the formalism for it. Big omega of a function f of n is the set of all functions that satisfy the following statement. There exist positive constants call them D and capital N such that for all little n greater than or equal to big N, the function that we're bounding is greater than or equal to D times the function that we're using to bound it. And that's a major definition that you should memorize. So I'm putting it in a big box. Now this looks probably pretty familiar because it's a lot like the definition of big O. There's just one important difference. With big O, we had a less than or equal to sign. So what that means is that we use big O notation to provide an upper bound on a function. It says your function, t of n, never gets bigger than this. Big omega is kind of the reverse. It's a lower bound on a function. It says your function is at least as big as this as the asymptotes go off to infinity. So omega is the reverse of big O. What do I mean by reverse? Well, I mean that if your function, t of n, is in big O of some other function, f of n, then f of n is in big omega of t of n, and vice versa. If the latter is true, then the former is true as well. So if you have two functions in a big O expression, all you have to do is switch the functions around, change the big O to a big omega, and it's still correct. So let me give you some specific examples of things that are in big omega of something else. 2n is in big omega of n, and it's in that class precisely because n is in big O of 2n, and vice versa. And likewise, n squared is in big omega of n as well, because n is in big O of n squared. And n squared is in big omega of 3n squared plus n log n, because that complicated expression is in big O of n squared. And so on, you can go on like this. Again, omega gives us a lower bound on a function. Just as big O gives an upper bound on a function. So big O notation says your algorithm is at least this good, and big omega notation says your algorithm is at least this bad. Now sometimes you can have both. Or you can have both an upper bound and a lower bound for something. So if t of n is in big O of one function, f of n, and it's also in big omega of another function, call it g of n, then Tn is effectively sandwiched between these two functions. It's sandwiched below c times f of n and above d times g of n. And if f of n and g of n happen to be the same thing, then we introduce a new notation called big theta. So in other words, for me to say that t of n is in big theta of f of n, I have to have an upper bound and a lower bound proof, and the upper and lower bounds have to match asymptotically. So formally, big theta of f of n is the set of functions t of n that are in both big O of f of n and big omega of f of n. And that's the third definition that you should commit to memory. Now, one thing you might wonder is, how can you have matching upper and lower bounds? How can you have a function that's sandwiched between another function and itself? Well, the answer is you get to pick different constants for c and d. So let me draw you an example. The horizontal axis here is n. The vertical axis will be our functions. And here's the origin. Suppose I want to show that something is in big theta of n. Then I choose maybe one low slope. Let's say d times f of n is 2n. I'm choosing f of n is n, and I'm choosing d equals 2. Maybe I have another one with a much bigger slope because I set c equal to 10. Now, if I have any function that fits between this lower linear line and this upper linear line as n goes to infinity, then that function is in theta of n. So I'll just draw one here. Maybe it gets off to a bad start. It's not initially between the lines. But if it stays between the lines for the rest of eternity, as n goes to infinity, then that function, t of n, is in big theta of n. Are there questions about this? Yes, sir. Well, that's how I've drawn it for now. So the way I did my definitions was in last class. I gave a definition for big O where I used the function c times f of n as the upper bound. And today I'm using d as my variable for the lower bound. So d times f of n is my lower bound function. You don't have to use the letters c and d, but that's what I picked. Exactly. We're saying it'll never be slower than this, at least once we get past this point for large values of n. And we're saying it'll never be slower than this. Other questions? Okay. So even though it wobbles a lot, this is effectively a linear time algorithm. One thing you should know about theta is that it's symmetric. So if f of n is in theta of some other function, g of n, then g of n is in big theta of f of n. So to give you some examples, n cubed is in big theta of 3n cubed minus n squared. And the reverse is true as well. 3n cubed minus n squared is in big theta of n cubed. But since for a function to be in big theta of some other function, the other function has to be both an upper bound and a lower bound, that means that, for instance, n cubed is definitely not in big theta of n, because n is not an asymptotic upper bound for n cubed. So that's a no-no. And the reverse is true as well. N is not in big theta of n cubed, but for the opposite reason, because n cubed is not a lower bound on n. Now, one thing you might recall is that you have to interpret big O notation a bit carefully. Like, for instance, n is in big O of n to the 8th. So if I say that an algorithm runs in big O of n to the 8th time, that's not a guarantee that the algorithm is slow. It could be that it runs in n time, and it's true to say that it runs in big O of n 8th time. It's misleading, but it's true. But theta notation can't be misleading in this way. So n is most definitely not in big theta of n to the 8th. So if I say your algorithm runs in big theta of n to the 8th time, it really is slow. Question? Oh, any questions about that? Another thing I want to point out is that there are some functions that are not in big theta of anything simple. So just to give you kind of a pathological function, let's look at f of n equals n times 1 plus sine of n. What does this function look like? Basically, I take a sine function, I add 1 so that it never goes negative, but it keeps oscillating back and forth between 0 and 2. And then I multiply it by n so that I get something like And so what's interesting is that you can have functions that oscillate back and forth between something that grows slowly or not at all at the bottom point and something that grows fast at the upper point. So this weird function here is in big O of n, and it's in big omega of, well, 0. It's about the best you can do, because it always returns back to 0. But it's not in big theta of n, or big theta of 0, or big theta of anything simple. You could say that this function is in big theta of 2n times 1 plus sine n, but that's not a simplification. So this function, that's reduced about as much as it can be. But you don't see running times of algorithms that look like this very much, but you should still understand that not everything has a simple big theta. And finally, I just want to remind you guys again that these notations, big O, big omega, big theta, are always independent of what function you're representing. So big O doesn't always mean worst case running time. Big omega doesn't always mean best case running time. You always have to ask what function is being bounded when you use this notation. Any final questions about this before I go on to algorithm analysis? Yeah. Oh, yeah. Well, you can definitely derive big omega and big O from theta because of this statement. So if some function f of n is in big theta of some other function g of n, then that immediately implies both that f of n is in big O of g of n, and it implies that f of n is in big omega of g of n. In fact, that's basically what it means. It's another way of rephrasing this. Other questions? I want to talk for the rest of the class about how to analyze algorithms. Not that there's really a how-to. It's basically as hard as any mathematical problem there is, in a sense. But most algorithms that you look at are not very hard to analyze. It's a matter of going through the loops, seeing how long each operation takes, seeing what loops are nested within each other loops, and so on. But I'll give you at least one exception as well. So let's start with a relatively simple problem, albeit interesting enough to be not totally trivial. So you're given a set of points. There are p of them. Maybe they're in the plane. Maybe they're in 3D space. It doesn't really matter. What we want to do is we want to find the pair that's closest to each other. So I want to give you an algorithm for this problem, and then we'll see how fast it runs. Basically, we're going to exhaustively try every pair. We're going to calculate the distance between every pair. And after we've calculated all of these distances, we're going to output the minimum that we found. And by the way, if you're wondering, this is not the fastest algorithm for this problem, but it's an algorithm, so let's look at how fast it runs. Well, first of all, we need to know how many different pairs there are. And I don't know, hopefully most of you have seen enough math to know that the number of pairs is p times p minus 1 over 2. And so that's quadratic in p. Now, each pair needs to be compared and have their distance calculated, but calculating the distance between a pair of points takes constant time, basically, if they're just 2D or 3D points. So each pair takes constant time to examine. And so basically you just expand this out, and that gives you the running time, which is in theta of p squared. Now, it's in big O of p squared because all the algorithm does is examine every pair once in constant time, and there are fewer than p squared pairs. It's also in big omega of p squared because the number of pairs we do examine is about half of p squared, and we have to do every pair at least once. So that's both the upper and lower bound on the best case and worst case running time, all right there in one expression. So in this particular case, you can figure it out just by looking at the code, which I will put up for you. It's probably not worth copying this down, but I want to make a few points about just how you can look at a code and without looking at it too closely, usually you know the running time because there are two loops. There's one loop nested inside the other. So here's an outer loop, and it's very clear that this outer loop iterates p times. Once for each point. And then the inner loop, well, the inner loop is runs a little less often. The inner loop only runs over the points that have a bigger index than the outer loop, because there's no use investigating every point twice, and you don't want to compare a point with itself. So this iterates on average about p over 2 times. Because on average, we're halfway through the list, and so we have to check out all the points with a bigger index than the one that's halfway through the list. So ultimately, what you do is you just multiply that together. You have p times that you iterate p over 2 times. So you just multiply each level of nesting in your loop, and that gives you theta of p squared time. And by the same token, if you had an algorithm that required you to examine every triple of 3 points, then that would take theta of p cubed time. But having done this, let's look at a counterexample that might fool you. So here's the second problem I want to look at. It's one which hopefully is deeply familiar to you, so I hope you'll understand this example. It is called Smoosh, and it's from Homework 3. And what makes Smoosh interesting is that any way to write it I can think of uses a doubly nested loop, very much like the one we just looked at, and yet it runs in linear time if you did it well. So algorithm number 2. Here's my solution to Smoosh. And the point is, once again, we have an outer loop that looks like it iterates up to p times. Well, if you just look at it really fast, actually, you might think, well, we set it to 0, and then we keep iterating until I reaches the length of the array. So maybe it's kind of obvious that it iterates p times. But actually, it's not obvious because the loop counter gets incremented in the inner loop, not the outer loop. So something a bit strange is going on here. Now, it's true that the outer loop might iterate p times. If every item in the list is different, then it will. Likewise, there's an inner loop. The inner do loop might iterate p times as well. If all the items in the list are the same, if it's a list of 3s, then that inner loop is going to iterate p times. It's going to compress all of the 3s down into 1, because that's what it does. So we have an outer loop that could iterate p times. We have an inner loop that it could iterate p times. The obvious thing to do is multiply p by p and say it's a p squared algorithm, but it's not. It's a linear time algorithm. And the reason it's linear time is every time we iterate the inner loop, I increases by 1. And as soon as I gets big enough to be greater than inst.length, both the inner loop and the outer loop can't go on any longer. So looks can be deceiving. And again, the running time of this algorithm is in big theta of inst dot length. So you might wonder, is there some formula we can apply to analyze algorithms and be sure of what their running time is? And the answer is no, I'm afraid. There's no surefire formula that always works. And in fact, analyzing an algorithm can be arbitrarily hard. And there are mathematical proofs that analyzing algorithms can be arbitrarily hard. And in fact, I can give you an algorithm whose running time depends on whether or not the Riemann hypothesis is true. The Riemann hypothesis is a famous unsolved question in mathematics. So until you can solve that question, you can't analyze my algorithm. And you can do this with pretty much any unsolved math problem. It's one of the weird things of computer science or complexity theory. So there is not a general formula, I'm afraid, for analyzing every algorithm. You have to look at this and you have to really think about it. And for some algorithms, you have to think harder than others. And you can spend a whole career as a computer scientist just studying and researching the analysis of algorithms and how fast they run. Are there any questions about this? All right. I also want to talk a little bit about analyzing running times that might depend on more than one variable. Or more generally, what are the big O relationships between functions of several variables? So here's problem number 3. Let's write a program to do matchmaking. And suppose we've got W women in our database and M men, and we're matching them up. And our algorithm is pretty simple. It's just exhaustive comparison. So just compare every woman with every man and decide if they're compatible. And I'm going to assume that comparing one man against one woman to decide if they're compatible takes constant time. They might have a different story, but so now, hopefully it's pretty obvious why the running time let's call it T of W comma M is in big theta of WM. The number of women times the number of men. Okay, so what does that mean, though? Well, what it means is there exist constants. call them C, D, capital W, and capital M, such that D times W times M is less than or equal to our function, which is less than or equal to C times W times M, for every big enough W and every big enough M. So that's the definition. The main thing I want to impress on you is that this function t is definitely not in big O of W squared, for instance, or big O of M squared, or big omega of W squared, or big omega of M squared, or all kinds of other things that depend on only W or depend only on M. That these functions are really incomparable with each other. And so each of these possibilities are eliminated either by choosing a database that has way more women than men, or by choosing a database that has way more men than women. So if you think that Wm is in big O of W squared, well, that's not true if you choose M to be way, way bigger than W. So the bottom line is you just cannot asymptotically compare these functions and say one dominates the other. Unless you know something special, like you're told that there's some constraint in the problem that you can't have more women than men, then you could do this. But in general, you can't. Now, to give another example of incomparable functions, suppose that we expanded our service so that in addition to doing matchmaking, it formed women's volleyball teams as well. Then now the running time is in big theta of W to the sixth plus Wm. So we're doing both functions. And again, the point is that these two functions aren't asymptotically comparable with each other. So you can't simplify this expression any more than this. You can't drop one of these two terms out because you don't know which one's going to be bigger. You know, if W to the fifth is bigger than M, then this term dominates. But if M is bigger than W to the fifth, which is possible because there's a lot of desperate men out there, then this term dominates. So this just cannot be simplified. Question in the back. With M cubed? Well, okay. It is true that yes, if I had theta of W to the sixth plus Wm plus M cubed, it is true that I could drop the Wm term. But I don't want to do the algebra right now to explain to the rest of the class why that's true. But the short story is, one of these has to asymptotically dominate this. You don't know which one, but you're guaranteed that this is going to be asymptotically smaller than at least one of these two, so you can drop it. Again, I don't want to do the algebra to prove that. Ask me in office hours or something if you care. Another thing I want to mention is that on virtually every exam, like final exam and often on midterm too, I give a problem where there's more than one variable involved and ask someone to analyze the data structure. I say, R is the number of items and K is the output size. What's the running time of the algorithm? There's always someone who writes down theta n squared or something like that. And it's like, hello, n is not one of the variables. There is no n in this problem. So everybody, when you do a problem on an exam, please check what the name of the variable is before you write down an n. It's not always n. Let's look at another problem. All right, you have an array, and it contains n music albums. And they are already in sorted order. They are sorted by title. And the problem you want to solve is you request a list of all the albums whose titles start with the best of. Now, I don't know about your record collection, so we can't know in advance how many such albums there are in your record collection. So let's just say that there are K of them. We don't know what K is, but we do know, obviously, that the running time of our algorithm is going to depend on K, because at the very least, we have to print out every one of those K albums. And it's going to take at least K time just to print them out. So here's the algorithm for doing this. Well, we're going to search for one matching title. With binary search. So we already know how to do that. And remember, n is the total number of music albums. We know how to do binary search in log n time. Once we've found one hit, we can find all the others because they're all adjacent to each other in the list. You just have to sort of walk in each direction from the first hit until you run out of the best of albums in each of the two directions. So just search linearly in both directions and stop as soon as you hit an album that is not the best of, and print off all the ones you pass over that are the best of. So that's our algorithm. So the running time of this, the worst case running time, well, I know it's in big O of, well, we know that binary search is never slower than log n time. So that's a good start. It takes at most log n time to do the search. And then we have to actually list off the K record albums plus, a couple extras at the end that aren't the best of. But basically, it's going to take K time. Once we've found one the best of album, it's going to take K time to identify and print out all of the other ones. And since that's all we do, the running time of our algorithm is in big O of log n plus k. Now, we also want a lower bound. In the very worst case, we can construct a case where it will take log n time just to find an album, like if we only have one album called, well, if we have no albums at all called the best of, then you know it will take log n time. And we can certainly construct an example where it's going to take at least k time, because if you have k record albums, it always takes k time to list them all. There's no way to avoid that. So this is a lower bound as well, so I can change that big O to a theta. But that's the worst case running time only. The best case running time is different. Now, the thing about this is that this cannot be simplified. And the reason why is k can be as large as n. Maybe you only buy albums that start with the best of. Or k could be as small as 0. So we can't say which of these terms dominates. If k is as large as n, k definitely dominates log of n. But if k is 0, then log n definitely dominates k. And we don't know in advance, before we search the array, how big k is going to be. So this is basically the tightest expression we can give in terms of n and k of the running time. So there's no simpler expression for the big theta. In terms of both n and k. One of the things that's interesting about this is that part of the running time depends on the output size, not the input size. And there's a name for that. Algorithms are called output sensitive. If the performance depends partly on the size of the output. Now, having said that, I said that the best case running time is not the same as the worst case running time, because we all remember that the best case running time of binary search is when you happen to get lucky and you have a hit on the very first item. So the best case running time is in big theta of 1, you get lucky with the binary search, plus k. You don't get lucky with printing all the album titles. You still have to print out every one of them, and that's still going to take k time. But as a general rule, as k goes to infinity, obviously it dominates 1. So you can simplify this expression because you don't need the 1. Any questions about that? All right. Well, that's it for today. See you next time.